Hey geometry kids, this is 4-6. This is the last section of the chapter, I think. And this is on symmetry, and this should be one of the easier sections of the chapter. This should be a lot better than the last couple sections that we've had, hopefully. So in the section of symmetry, there are two main types of symmetry that we'll talk about. One of them is line symmetry. And I know we hit on this like in chapter 1 when we briefly went over symmetry. But the first one is line symmetry. And then the second one is down further a little bit, is rotational symmetry. And so we'll talk about both of those. So two main kind of like big ideas of this section. So back to line symmetry, a figure is going to have line symmetry basically if you can fold it in half and it like folds on top of itself. So like this figure here, he has a line of symmetry here because I could take this and fold this down and it would like map on top of itself. Okay. I a lot of times talk about like in elementary school when you had like a piece of paper and you would like fold that piece of paper in half right here and you would like paint something, whatever, on this side and then fold it in half. It would end up being like the same whatever type of thing on the other side. Okay, or close to the same thing. That's kind of what you're looking for when you're looking for line symmetry. That fold down the center is going to be your line of symmetry. Now, some figures can have multiple lines of symmetry, like this first object that we're talking about here. This is a pentagon. It has five sides. It says determine whether the figure has a line of symmetry. This one does, and in fact, it has like a bunch of them. My first line of symmetry I can think is this first one down the middle. It's the same on both sides. If I fold him then, though, instead here, he would have a line of symmetry. So like this little bit is the same as this little bit. Okay. If I instead folded him here, where this half and this half were the same, that would work as well. And then I have a line of symmetry here, where this chunk and this chunk is the same. And then the last line of symmetry I have is right here, where this top chunk and this bottom chunk are the same. Okay, so I hope that was kind of a little bit easy to see. When you go to count the lines of symmetry, okay, if you don't count them as you go along, a lot of people end up double counting them. They're like, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Lines of symmetry. Well, that is not quite right because these last 5, like this line is going all the way through. So don't double count it, right? Like that's only 5 lines instead of 10 lines. Does that make sense? I know that maybe that sounds stupid that would even be a thing. So if you're one of those people that's like, why would they double count? Like I've seen it a lot happen. So I'm just warning you, if you're one of those people that, that's not obvious to you that that's 5 lines, don't double count your lines. So 5 lines of symmetry. And that's appropriate because this is a pentagon, a 5-sided figure. Okay. B, lines of symmetry. I could try to draw a line of symmetry like here maybe, but this isn't going to fold on top of that because this is a scalene triangle. If you want a vocabulary word here. Scalene means none of the sides are going to be the same. If this was an isosceles triangle or an equilateral triangle, maybe it would be a different story. But we're not going to have any lines of symmetry on this one because it's not going to be mirrored on any of the sides. So 0 lines of symmetry, not going to be the case. Okay. All right, down here, like if we go through these, the check really fast, this figure is going to have 2 lines of symmetry, one right here where I fold it, and then one where I fold him like hot dog style, right? Hamburger or hot dog style, it's like a piece of paper, right? I cannot fold him diagonally. Okay, this is hard for people to see as well. If I try to fold him diagonally, right, and I map this guy, like let's say I would fold him over here, what would happen is I would end up with a shape that it does one of those, right? Like this would be mapped over to here. So like in other words, if I were to fold him diagonally like this corner would not touch this corner because it would be like down here. I don't know if that's hard for you to see, but the fact that it's a rectangular shape and not a square shape makes it so that it will not fold on top of itself, right? Like if it was a perfect square, it would do that, okay, where this would touch here. But the fact that it's a rectangle won't do that, okay? So this figure only has 2 lines of symmetry. The diagonal one does not work, okay? This one is an equilateral triangle. He has 1, 2, 3 lines of symmetry. Okay, this is a trapezoid. And if I try to fold him like down the center, because he's like longer on this side than he is over here, he won't have any lines of symmetry. So hopefully that's a little bit more obvious to you. He will have 0 lines of symmetry. This one down the middle will not work. And that's lines of symmetry. I don't know how much more I can dive into that. Okay. The next thing is something called rotational symmetry. And we've talked about the center of rotation. Like, I think I stood in the classroom at one point and I was like, if we rotate us in the corner, you know, our classroom will end up like in the hallway, versus if I stand in the center of the room and I rotate, the people at the front will be facing the back and the people at the back will be more toward the front, you know, like the center of rotation. If I rotate over here around this dot, like my square is going to rotate around that way, versus if my center is in the center of the classroom, like I'll just rotate like this way. Does that make sense? So your center of rotation is very important. And for the majority of these, our center of rotation is going to be like in the middle of our object. Okay. You're not going to have any centers of rotation that are over here where you're rotating like over this direction, whatever. Okay. So center of rotation is inside of the figure. And then we've got to talk about order of symmetry, which we haven't ever done before, and magnitude of symmetry. So we're going to do that here in just a second. Okay. So let's talk about, this shape. This is a square. And our center of rotation is right here. Okay, we're talking about the order. Let's do this. Order and magnitude. We know that this guy is going to have rotational symmetry. If I rotate him around, he will land on top of himself, right? Like if I take this and I rotate him and this dot moves to here, and this dot moves to here, and so on and so forth, he will rotate around and he will spin and look exactly on top of himself, okay? The order of what we're looking for is how many times does he land on top of himself before he returns back to the original. So like this dot could move to this dot, right? Or if I rotate him again, then he can move to this spot. Then he could move to this spot. Then he can move back to the beginning. So his order is 4. He can rotate 4 times around before he gets back to his original position. I hope that makes sense. Okay. The magnitude is how many degrees does he rotate from here to like there? Like how many degrees is that? Okay. And the way that we can figure this out is that rotating all the way around is 360 degrees. Okay, if I go one full circle, 360. Well, if my order is 4, all you have to do to find the magnitude, they have this little formula right here for you, is the magnitude is taking 360, a full circle, and dividing by 4, or the order that I have. 360 divided by 4 is 90 degrees. So that means that going from this dot to here is a 90-degree rotation. Okay, so magnitude is 90 degrees, order is 4, and that's how that works. Okay, let's do another example. So let's go to, rotational symmetry is also called point symmetry. A figure has point symmetry if it can be mapped onto itself by a rotation of 180 degrees. So I think point symmetry is specifically 180 degrees rotation. Like this diamond right here is not the same thing as as the square that we just looked at, because if I try to rotate this guy just 90 degrees, he will end up doing, I don't know, one of these. Right? He'll be longer than he will be tall, right? So he won't have an order of 4. He will only have an order of actually 2, right? This dot would have to rotate all the way around to here in order for him to be on top of himself. Does that make sense? And then rotate again. So he has point symmetry because you can flip him upside down or do 180 degrees, and then he will land on top of himself. I hope that makes sense. Okay, so that's what's called point symmetry. Point symmetry is specifically rotation of 180 degrees. Okay, this one is just specifically 90 degrees. Like that's what he would be, as 90 degrees. So this one technically does have point symmetry, but he has more than point symmetry. He has a 90 degree magnitude instead of 180 degree magnitude. But he still has point symmetry because you could still rotate him 180 degrees and he would still work. Okay. I hope that makes sense. Example 2, identify any rotational symmetry. Okay, so we have this leaf, and he does kind of have, he kind of has a line of symmetry, but that's not what we're talking about here. We're talking about rotational symmetry. So can I rotate him and him be like mapped on top of himself? Well, even if I flip him upside down, where like the leaf goes here and here, and then here, and my stem would be like there. That's not going to work. That's 180 degrees flipped. That would not work, okay? So this one is a no. He has no rotational symmetry. Okay, this flower, assuming it's like all the petals are exactly the same. I have 1, 2, 3, 4, 5, 6, 7, 8 petals, right? So I could rotate this petal from here to here. I could rotate from here to here. I could rotate 8 different times to get back, and like he would map on top of himself. Okay, so that's my order. So he is a yes, first and foremost. Maybe we should designate yes. His order is 8 because I could rotate 8 different times because he has 8 petals. Okay, the order is 8, and then the magnitude would be how many degrees it takes to get from here to here. Okay, to find the magnitude, I take 360 and I divide by 8. And that is like 45 degrees, I think. So it takes 45 degrees to get from here to here, okay? It takes 90 degrees to get from here to the second petal, right? Like that looks like a 90 degree whatever, right? So that's how that works. Order, magnitude, he is a yes for rotational symmetry. Order 45, or order is 8, magnitude is 45, okay? All right, this is my 4-leaf clover. If I pick a point, let's pick like this, I don't know, like little heart-shaped looking thing, okay? I can rotate him from here to here, or I could rotate him from here to here, or here to here, or back on top of himself, right? So his order is 4, right? Or if you can notice that there's like 4 little petals, order is 4. Magnitude is, again, 360 divided by my order, which is 4, and that's 90 degrees. So it takes me 90 degrees. So he is a yes, and he has an order 4, a magnitude of 90, okay? And that is example 2. Let's go to example 3, determining order and magnitude. State the order and magnitude, determine whether each figure has, didn't we just do this? Oh, these ones were just supposed to be like, do they have rotational symmetry or not? Sorry. I did more than we needed to. Now we're going to do order and magnitude. Blech. These little lines. Do you remember what those little lines mean? Those little lines mean that like this length is the same as this length is the same as this length. So we have a pentagon that has all of the sides equal. And I guess if all the sides are equal, all the angles are going to be equal as well. So this is what's called a regular pentagon. Okay, regular means all of the sides and all of the angles are the same. So just remember that from a couple sections ago. Regular pentagon, okay? So we can rotate him, and I always pick like a point right here, like this point, that vertex. I can rotate him to this spot. I could rotate him to this spot. I could rotate him to this spot, or this spot. Okay, that is 5. His rotational symmetry, he is a yes. He does have rotational symmetry. His order is 5. Now his magnitude, I would have to take 360 and divide by 5 to get the magnitude. And it may come out, some of these might come out as a decimal actually. 360 divided by 5 though is 72 degrees, I think, is what he comes out to be. So basically to get from one vertex to the next vertex, I have to rotate him 72 degrees to get him from there to there, okay? B, if I put my center of rotation in here, okay, and again, the center of rotation for this pentagon would be right there, okay? Center of rotation here, like this vertex, if I rotate him around, like he would be, I don't know, he would look like this instead if I rotate him around. So he does not have rotational symmetry. He is a no, right? Like, do you see how that works? Like, it's not going to perfectly match on top of himself, okay? So we don't have to do order and magnitude because he doesn't have rotational symmetry. Okay, C, these little arrows mean that those two guys are parallel and these guys are parallel. Now, we do not necessarily know that like this length is the same as this length right there, okay? So if I were to rotate him, we would not necessarily, he almost looks like he's longer this way than he is this direction. So I'm going to guess that if we rotate him like just from here to here, right, he's going to like be standing up and be taller, right? Like something like this. I don't know. So in order for this to have rotational symmetry, we would have to spin this guy, like this vertex would have to come to this point, and he would have to be like spun 180 degrees. I hope that makes sense. Like if I just spin him from here to here, he's going to be taller, right? And go like that, okay? So that's not going to cut it. I have to spin him to this vertex and then spin that one to this guy, okay? So he does have rotational symmetry. That is a yes, but his order is only 2 rather than 4, right? And that's just because he's longer in the one direction, okay? So 360 divided by 2 means his magnitude is 180 degrees. So he has rotational symmetry, but he also has what's called point symmetry, okay? Because that's 180 degrees for his magnitude, right? Point symmetry is what he's called, okay? Which figures in part A have point symmetry? Justify your reasoning. We just talked about that. This is 180 degrees. So, C, that's a parallelogram. Parallelogram. That parallelogram has point symmetry. Now this pentagon, okay, we rotate 72 degrees to get him on top of himself. So he will not have point symmetry because if I rotate him 180 degrees, right? Like if I flip him upside down, basically, flipping him upside down would do this. I'm trying to draw him. I don't know. I'm really bad at this. That's what he would look like if I flip him upside down. Like his, would be facing upside down. That's not going to work. So he does have rotational symmetry, but he does not have point symmetry. Okay. And this one doesn't have either one because he just is weird. So C is the only one that has a point symmetry. Okay. I hope that made sense. Maybe. And maybe that's a little bit easier than what we've been doing. So hopefully this is a little bit of a break. Homework 1 through 14 all on page 297 or 279. Hopefully that was okay, and I'll answer any questions tomorrow if you have them. I think on all of these figures, if they look like the sides are the same, then the sides are the same. Like I think you can conclude that this is an equilateral triangle and all of those sides are the same. So if they look like they're the same, I think you can assume that they are. Okay. All right. Like this one does not, these sides don't look the same. So I don't assume that any of those sides are equal. Like this is not the same as that one. Okay. So, yeah, just be careful about that. Whatever. Okay. 1 through 14 all. There you go.